So yeah, I can see someone's doing that. So I'll just enlarge what I was saying. So there is my work for the first one, and I got 20.151, and my work for the second one as 0.551, and my work for the third one got negative, really small number here, negative 0.04961. And so this will be at your disposal. If you need to go back and check your solutions, you can just come here and check them. But I'm going to go and show you these answers on the Desmos part here. So let's just change the function. So the function here was negative 4.9 t squared. I'll just put x plus 30x and no plus 4. So of course you can see it's a little zoomed out here, but there is the shape of what's going on. And the first question I asked you to look at x equals 1. So that means the a value here is 1. So I'm going to move it to 1. Okay, so there's the a value, and the h value I have right now is also 1, so it's pretty big. And you can tell already as I increase the h, the steepness of the blue curve is not a very good representation of what's happening of the red curve. The blue line is not a good representation. So we shrink this down so that the secant starts to look more and more like the slope of the red curve. We can see we're getting 19.2. I can shrink this down to 0.1 and we get 19.71 as a pretty good estimate. And then what we calculated was an h of 0.01, and then there's the number we calculated, 20.151. So if we had to estimate what the IROC, the instantaneous rate of change, would be, I might guess something around 20, because you can see as I shrink this down, it's getting closer and closer to 20. Let's actually find out. So I'll turn on the secant. And oh, it turns out that the slope of the secant is 20.2. So it's actually getting closer and closer to 20.2. Let's go back and increase my h value. So you can see, actually, I should have noticed this. The numbers are actually getting steeper, which makes sense. So as we get closer and closer to our number is getting a little bit bigger. So get that, and you can see it's 20.15. If I put a bunch of decimals, really shrink that, you can see now it's getting closer and closer to 20.2. Put in a bunch, we get, yeah, it's getting really, really close to 20.2. And so the slope of the tangent actually is 20.2. Now this is one of the problems with using the secant version to estimate IROCs is, even though you can kind of see it getting close to a number, if you're not really, really small, it's hard to see what that exact number is. And if the slope is something like a decimal, it's even harder to tell what it is. So all we can do is get pretty good estimates. Let's go back here and do the second question. So the second question asked us, I'm just going to turn off the tangent. The second question asks us to investigate at x equals 3. So I'm going to move a to 3. A is 3, good. Okay, and we're going to put this at 0.1. Okay, and you see the steepness here is it's almost 0, I would say. If made it even smaller to the point we calculated, there it is. Slope was 0.551. And as we make this even smaller, you can see it's getting really close to 0.6. So I'm going to guess that the slope of the tangent here is 0.6. It's still positive, but it's pretty close. So let's check. Yep, there's the slope of the tangent is 0.6. Okay, so the numbers are getting closer and closer to it. And then this back. See, when the H value is 1, it actually starts to go down the other side of the curve. And so that's why it's not a great representation of the slope at 3. I'm way too far away from 3. My secant is way too far away from 3. Even when I get something like this, which is pretty close, it's still a negative. And when the reality is when you get really close, it switches over and becomes positive. All right, so let's go off now and try this new H value of, or A value of 3.061224, which seems kind of out of the middle of nowhere. And again, if you do the math, you start to see that it is 0.048999. Okay, it's getting really, really small. And if you see the secant and the tangent are about the same, it almost looks 0. Looks like it's going to 0. The slope here looks like it's almost 0, 0.0048. There's the tangent. So if I shrink this, I should get closer and closer to that number. Oh, too far. There we go. 0.0044. The actual slope of the tangent is 0.000048. Okay, so I think it's safe to say we're getting really, really close to 1, or sorry, to 0, which means we're getting really, really close to the top of this function. And but we're not there yet, and that's what you're going to investigate in, and maybe you already have, investigate in the second half of the other Desmos activity we did this morning. Okay, so that's enough playing around with that for now. We're going to move on to a new Desmos activity. So I'm just going to stop presenting here. So I'm just going to pause the other Desmos activity and go and release this new one. Okay, if you go to Google Classroom, you'll see a new Desmos activity called Investigating the Behavior of Slopes and Tangents. So I'll give you a second to get over there. Okay, I'll just sort of walk you through the first few to show what we're doing, and then you'll go off and try this on your own. So where are we here? Okay, so you'll see now that instead of talking about secants, I've drawn tangents, the slopes of the tangents. So we understand that if we shrink the secants, we'll get to tangents. Now, we don't know how to calculate the slopes of the tangents. That's why we're going to Desmos, okay? But what we're going to do now is start to notice some patterns about slopes of tangents. So for example, what we do here is you see that I've got this tangent here that you're going to slide up and down the curve, and you're going to go to different spots. So the first spot I'm asking you to go to is -2. So you're going to slide this so that x is equal to -2. There it is, -2. And I want you to record what the slope of the tangent is, okay? Not the y value. So if we put in the y value, you'll see an error. Now the error is actually at the bottom, so you might not be able to see it, but you're not putting in the y value. Don't tell me where the curve is. I want to know how steep the curve is. And it says at -2, the slope of the tangent is 10. So the first one is 10. Okay, and then you're going to move this cursor up to the next x value. X is 1. Again, I don't care about the y value. I want to know how steep it is at 1. And it turns out the slope of the tangent at 1 is 8. And then continue on, move this to 0 and 1 and 2 and 3, and record all of the information in here. Okay? And then there'll be some other questions coming up that you haven't seen that asks you to investigate what's happening. Okay, so I'll give you a couple of minutes to go along here. Stay in the Google Meet so I can monitor how we're doing. But I'll release it a little bit more now. Just so you know, on some of the slides, there's more information below. So if you're in the Google Meet right now, you'll see I'm on a slide. Actually, I'll just anonymize that, sorry. So I'm on a slide, and like the table that you calculated is right there. So if you needed to go back and forth, you can go see the table at the bottom. And so just sort of scroll that. You'll be able to tell there's more stuff on the slide if you see this toolbar down on the bottom, this drag bar. So just something to help you out. So just a minute or two left on the Desmos activity, and then we'll come back together. Okay, so I'm just going to summarize what you hopefully discovered there. And actually, looking at your answers, I discovered that some people saw one thing and some people saw another thing, and both of them are correct. So I just want to clarify what's going on with those. So let's head into the activity here. So, so early on, you calculated all the slopes. And then I asked you to look at when the slope was increasing, or sorry, when the original graph was increasing. And what did you notice about the slopes? And I saw two different answers. One, I saw this. It said, as the slope, or as the original function is increasing, the slopes of the tangents are decreasing. And that is true. If you look at these slopes are decreasing. Now, that isn't what I was thinking you would say, but actually makes total sense based on my wording. As it's increasing, the slopes of the tangents are decreasing because this is a parabola, an upside down parabola, and it's getting smaller. But sometimes as the slope increases, or as the curve increases, the slopes get bigger. So what I was hoping you would notice, and you can look here, is that as the slopes as the graph is increasing, all the slopes are positive. That's where I was going with that. But if you said that the tangents are decreasing, you're right. And that's a different characteristic. But what I was sort of getting at is everything here, if you watch this slope, all of these are going to be positive. Even this guy here, which is really close to the top, still has a positive slope. But then as soon as the graph starts to decrease, the slopes of the tangents are negative, which again makes sense because if the graph is going down, the tangents that represents that graph must also be going down and therefore negative. So where I was going with this was that as they're increasing, as the curve is increasing, the tangents are positive, and as the curve is decreasing, the tangent is negative. That's where I was going with that. And then I asked you to go and move it so that it's right at the top. And this, I can see that everyone sort of had the same idea in that the slope of the tangent is 0 at the top. So let's just go and see everybody's answer here. Yes, the slope of the tangent is 0. The absolute maximum red function, the slope is a tangent of 0, 0, 0, 0. Good. So we all picked up on that. Careful here. There is the slope. The slope is 0. Remember, no slope is this, a horizontal line. This is the slope. It has a number. The slope is 0. Okay, so it's not that there's no slope. The slope is 0. Okay. Oh, look, people are going to change their answers right now, which is funny. Okay, so so then what can you conclude about the slope of the mat at any maximum point is that the slope will be 0. So let's again go back and look at our picture. You can see that happening. So here is the slope. It gets really, it's negative, but it's getting smaller, closer and closer to 0. And then boom, the slope of the tangent is 0. Remember, 0 is this. Okay. Are there other spots on the graph of different certain other functions where you'll also get a 0 spot? So here we got a 0 at the absolute maximum. So let's see what people answered for that. So scrolling down here, are there other spots? Yes, the minimum point of a parabola will also be 0. Yes, minimum point. So some said not to my knowledge, but later on probably discovered that yes, a minimum would also get you a point of 0. And so if we go off and look at another function like this guy here, you can see then when it's increasing or decreasing, but the slopes of the tangents, let's get to the next slides where we actually have the tangents here. Oh, this person got the tangent off the screen. There we go. Okay, so let's look at the slopes of the tangents. Here, when it's increasing, the slope is positive, increasing, positive, 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 0. There's at a maximum. And it's called the local maximum because it's not the highest point of the function. Remember, over here is higher, but locally it's the biggest dog, right? It's the highest spot. So that's locally. And then as it goes decreasing into the purple section, it's decreasing. You see the slopes of the tangents are negative. negative down to here, and then boom, it gets back to 0. So again, you can see it gets here, the slopes are getting actually steeper, steeper, steeper until it's probably steepest right there. And then it gets steeper, it gets less steep, less steep, less steep, less steep, back to 0. So minimums would also have a slope of 0. And then of course it starts to get bigger and bigger and bigger. This is increasing, and you see in this case, the slopes are increasing until you go off there. Okay, so that is the two things that we were hoping to discover. So there's the local max, the slope of the tangent is 0. And the local min, the slope of the tangent is 0. It happens, this one happens at 2. So again, not 2, -1. I don't care where, but the y right now, I just care that it happens at 2. That's the location. So the tangent is 0 when x equals 2. And so there's your local max, and there's your local min. Local max, local min happening there, and the tangents at both of those would be 0. And that's one of the big characteristics. Okay, so now you are on to another function, so I'm just going to release this. Okay, so now you can go on to slide 10 and look at a different function. Okay, just a minute left and then we'll come back. Okay, so if you are in the Desmos activity, that's fine, but I'm going to be presenting the Desmos activity and sort of pointing something out. So you might want to come back into the Google Meet to see what I'm pointing out in the Desmos activity. So I am here, and we have what you discovered in the first view, of course, is that as the function is increasing, the slopes are positive. As it's decreasing, it's negative. And at the maxes or mins, we get 0. The slopes are 0. So here I gave you a new function, didn't tell you what it looked like, and you just had to start to guess what the function looked like based on the slopes of the tangents. So I asked where you thought it might be decreasing. And so since it's decreasing, then the slopes would be negative. So since the slopes here is negative, 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 it looks like all the spots between 0 and 4 is where it's decreasing. Now, some people said 0 and 3, which is a good guess, or said between 1 and 3 because they're all negative. But I'm going to guess that between 0 and 1, they're also negative. And so that's why some people guessed 0 and 4. So then they went off here and saw that, yes, that part of the graph is negative. Then I asked if you were right, and I was expecting most people to say kind of, because you're kind of right in that you were able to show that this part is decreasing, but you didn't know about the other graph because it wasn't in the table, right? You didn't have information on the slopes of the tangents way over to the left. So how could you tell that those parts were negative? And so then when you actually see the graph, you discover, oh, wait, there's other spots where it's also negative, decreasing down here. So the slopes would be negative, 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 and then get to 0, and then positive, and then negative, and then positive. And then similarly, you can find the local maxes and mins by finding where the slope was 0, and there's the maximum. The struggle is real. There, oh, jeepers. There we go. The slope is 0, so you know you're at the max, and then the min is at -4. Okay, so the local min's at -4, and the other one's over at +4. So that was good. So the local mins are there. Now, be careful, because now we're asked to find the value of these things. So how big is it? So this is when we start to become interested in how low this graph goes. So I know that the minimum happens at +4. The question is, what is that local minimum? And the value of it is -32. Okay, it happens, it's the same in both of these. So -32 is the value of it. And the value of the maximum, well, it goes all the way up to 0, even though that's not very high. Okay, and then this was the challenging one, asking you to find, without the graph there, where the local minimum is. And the problem is you get really close, but you can't get right on there. So I would anticipate that most people will say that they can't tell me it. Let's see what your answers were for that. Yeah, I can't, good. And let's see why. So I can't find exactly where the slope is 0. The slider won't allow me to move there. That's right. I purposely decided it's somewhere between 2.2 and 2.3 exactly. Okay, so I made the slider so you couldn't get right on there. So that was a problem. So to help you, I said, okay, let's start putting in numbers. So let's click on someone here. So someone guessed 2.3, which you can see the slope is 0.06, so it's close. 2.2, oh, it's still there. So maybe 2.25. Oh, you can see you're getting closer and closer to 0. Maybe 2.4, 2.6. Oh, we're getting closer. 2.7. There it is. I found it. So 2.27 was actually where this graph hit its minimum value. So the X value was 2.27, and then you can now read that the min value is negative 4.9. So this function actually goes down to negative 4.9. So, but it does highlight some of the problems with just expecting Desmos to give us the answer. Like I purposely set it up, you couldn't, so you had to go closer and closer. And when the numbers get smaller and smaller, it's harder and harder to be accurate. Okay, but you knew you were right because the slope of the tangent is 0. So you know that that's got to be the minimum or the maximum. Okay, all right, so then you got a nice job. So I'm going to stop presenting here and go over to the other thing. So just give me a second. So, mic check, please.
Yeah, you're good.
Okay, good. I realized when I was presenting on the other one and doing that my volume was down. I did that to avoid feedback, but then realized I had my volume down everywhere and couldn't hear if anyone was asking me any questions. So, were there any questions with that Desmos activity that someone was trying to get my attention?
Not that I heard.
Okay, good. Thank you, Jacob. I know often people, if they're not being heard because I have the volume down or something, they type it in the chat, so keep that up. But it looked like there weren't any problems, so I didn't miss it. Okay, now those Desmos activities that I'm giving you, and then we still have lots more of them to do, they are like your notes, okay? Because as I said, normally we'd be filling out worksheets, so you're filling them out digitally online. So if you need to get information on what you're learning, go back to those notes. I do have a few notes that I'll do on the whiteboard here, but the Desmos activity, they'll be open. So if you want to go refer back to that and see what you learned, that's your notes, okay? But this is kind of just a quick little summary of what you discovered there. So this was the function that you first played around with, 6x minus x squared. And here are the slopes of the tangents. Yours was a vertical graph. This one's a little bit more, or a table. This one's a little bit more horizontal. But it does highlight the most important part of that. So you discovered, we knew that the graph was increasing from here, increasing. All the way up to x equals 3. So I have a little picture of the graph up here. You can see it's increasing all the way up to x equals 3. The graph is increasing all the way there. And you can see that when the graph is increasing, all of these slopes of the tangents are positive. And then the graph starts to go down. So you see it starts to go down after that. So here, this is decreasing. And you'll notice that all the slopes of the tangents are negative. And obviously between positive and negative is the spot where we're at our maximum. So this is increasing all the way up here. And then we get to our maximum, And our maximum is where it changes from increasing to decreasing. So it changes from positive to negative. And so here, the slope of the tangent at the maximum is 0. And similarly, if we were going to a minimum, you would see the slope of the tangent at the minimum is 0, because it'd be negative slopes getting to 0 and then going up and getting positive. So that's just a quick little summary of the investigation one that we had there. So this one you might want to throw in your notes. Just have it written down someplace maybe. There isn't a lot of notes here on the first day, but this kind of reviews what we did this morning and just finished up here right now. So we approximated the average rate of change by finding the slope of secants. So this morning we discovered what a secant was. We had 2 different slope formulas to find the slope of those secants. And as they get smaller and smaller and smaller, the estimations get better and better and better and more accurate. The slope formula that we landed on is this one. Okay, where A is the point that we're interested in, and H is some interval a little bit beside the point that creates the little secant. The smaller H is, the more accurate a representation of what the actual steepness of the curve is at point A. Okay, we've graduated from the grade 9 formula to this grade 12 version, and you'll see why in a bit. So we verified all of these secants on Desmos. We did it on the formula, and then we checked them all to see that we were right. And by taking smaller and smaller intervals, we can guess the instantaneous rate of change. We can make a guess at what that instantaneous rate of change is. So secants get us AROCs, average rates of change. Even though they're small, they're still average rates of change. And the smaller we get, will allow us to estimate or guess what the instantaneous, the IROC rate of change is at that specific spot. To be more accurate, or the most accurate, we would want the slope of the tangent, not the slope of the secant. But calculus, without 2 points, we don't know how to find the slope of this tangent. So we'll need some sort of calculus, and calculus was the big thing that got invented to get over this hurdle, to be able to find the slope of tangents. Okay, so this just sort of is one of the foundational ideas of calculus that I will build upon. And you're experiencing it through the graphs to imagine what's actually happening. Okay, all right, so now we're going to go back to Desmos. And we're going to do this next activity together. So we're going to go slide by slide and do it together. And I'll teach, because it would be like teaching on the smartboard, but I'm going to teach with the Desmos activities. Sorry about that. Okay, so I have released the Desmos activity called the Dragster Revisited, and I'm going to, oops. Okay. So I'll just turn the camera off, but I will go into the and I'll present my screen. So I am presenting my screen, but you'll probably be actually doing it in Desmos at the same time as I will be. So you don't necessarily have to watch in the Google Meet. You can just watch and participate in the Desmos activity with me. All right, let's just make sure everyone's here. Yep, everyone's in. Okay, so I'm on the first slide right now. All right, so on the first slide, remember from this morning, we have the function d equals 19t squared, and then if you push go, we see the graph, and the graph that we're looking at describes the distance traveled, okay, not the speed, the distance traveled. And then when we go to the second slide, we can find the slope at different points of the tangent, okay? So what I want you to do is, we're all on the second slide now, I hope. We're going to collect all of the different slopes and put it in its own table. So similar to what we were doing before, where we're collecting secants, but now we're collecting slopes of tangents, okay? So the beginning, your dragster should be at the start. You see that the slope of the tangent is 0. So the first one, the slope of the tangent is 0. Then you're gonna move your dragster over to 0.5, and of course it's starting to speed up. And so you should be able to read off your graph that the slope of the tangent at 0.5 is 19 meters per second. And then drag your dragster to 1 second, and it should tell you the slope of the tangent is 38. So I'll give you a second to keep going and putting in the rest of the slopes of the tangents at the different spots. So we should be on slide 2 right now. Cynthia, remember I'm calling you by your anonymous name. There we go. Everybody's on there. To see your anonymous name, it should be up in the corner of your Desmos screen. Okay, so everybody is on slide 2, and I'm looking at slopes of tangents. It looks like people have got different slopes of tangents. Good, good, good. Okay. All right, so we all have the different slopes of the tangents recorded into a graph, or sorry, into a table. All right, so now I'm gonna release it up to the next slide. So let's go to slide 3. And actually, let's just pause right here. So if you could come back to the Google Meet, please. So I just want to show what we're going to do here. So you see that I've graphed the first few of these. So what we're going to do is now take these slopes of tangents and put it onto the graph. So the 0, 0 spot is there, the 0.5 and 19, and the 1 and 19 or 38 spot is there. Then we're going to go to 1.5 and 57. So you're just going to estimate about where it is, and you're going to just move your cursor and push once, and you'll get a nice dot. And then 2 and 76, which is probably really close to there, right about there. Okay, so I want you to go off and do that. So I'll unfreeze you. So you can make those dots. And I'll also open up the next slide. Okay, so I'm on slide 4 now, and as I just sort of shuffle through, I see people have plotted all those points and sort of saw that they do go in a straight line, which is very curious. So if you graph all of the points of the slopes of the tangents, then it looks like they go in a straight line. Now, on slide 4, you only plotted the points between 0 and 0.5 and then 1 and 1.5, but I could have asked you to find the slopes of the tangents at even smaller intervals in between those, gone like, tell me the slope of the tangent at 0.1 or 2.99 or 3.8765. And all of those would have given us new slopes of tangents that would have followed this pattern. And then, of course, once you had that, you could connect these dots with a line that goes through all these points. And what we have here then is a brand new function. Okay, so let's pause this and come back to the Google Meet, please. Okay. So here I am on Albert Einstein's page. So we've discovered then if we take all of the slopes of the tangents and graph them, we get this new function. And you can see this new function happening, which in this case describes the speed, right? So the speed of the dragster must be increasing, and it's increasing at a constant rate in this particular example, okay? So what we've discovered here is a new function. So I'm going to the next slide, which you haven't opened up yet, but I want you to be here. So this new function, which describes all of the different slopes of the tangents at various x points, is a brand new function. And it has its own name. Does anyone know what we call the function that describes all the slopes of the tangents? Is anyone home?
I'm at home, yes, but I do not know the answer.
Okay, fair enough. All right, so this new function is a brand new function that describes the all of the slopes of the tangents, and this new function is called the derivative. And I'm sure we've heard of this word before. When you hear calculus, you hear derivative quite a bit. If you haven't, that's okay, it doesn't matter. But the derivative is what we are going to be spending the next 5 weeks, or no, I guess not 5 weeks, 3 weeks learning about, because it is this new function that describes how other functions change. And it is the derivative, okay? And so I'm going to open up and unpause this and allow you to go to the next 2 slides, including the 6th slide, which is a note that I'd like you to copy down. Japers, sorry. Not quite as sweet a setup as I had at Center Hastings, where I had a remote in my hand to be able to mute. I have to go back and forth, but I'm getting better. So we'll get this figured out. All right, so you don't need to copy this down. This is what's in the Desmos activity. You took all the information, you found the different slopes of the tangents. We plotted this new function, which describes the slope of the tangent to the curve at different x values, and that thing is called the derivative, okay? And so the definition that is in Desmos there is also written here. The derivative of a function, f, so if we start with some function f, the derivative is denoted with f prime, okay? So it's got a little apostrophe up there. It's only one apostrophe. It's called f prime, or f derivative of f. So you'll hear me say both of those. Both of those mean the same thing, but the little one tick is a prime thing in mathematics. So it's called f prime, or the derivative of f, and it's defined as this: for every x, the derivative is the instantaneous rate of change of the function at that x when the derivative exists. We're going to investigate this later on, I think tomorrow, about when sometimes the derivative doesn't exist. But for most times, the derivative, and then what we're going to study here at the beginning, the derivative does exist. Okay, so we're going to spend definitely the rest of this unit and next, well, everything in calculus is all revolves around the derivative, finding and explaining how functions change. Okay, so that's that note. Now, we're going to, that sort of completes 2 days worth of stuff. We're going to start, well, 2.5 days. This is the wrap up of day 3A. So now we're going to go back to Desmos to do our final activity of the day. And I'll leave you for that to finish off after 1:15. So I'm just stop presenting again here and go back to my computer. Actually, before I go, what we're going to be doing is this worksheet here. So we're going to be investigating the derivative of different common functions. Okay, so normally we would be doing this by hand and using Desmos as a guide, but I couldn't get this worksheet to you, so you're going to do the drawing on Desmos. Okay, we'll do one together and then I'll leave you to go off and do the other ones. Now, if you want, you can use this this worksheet. I'm going to release it in Classroom. So if you can, I don't know what your capabilities are, but if you can get it and print it off, then you could do that. Or it's a PDF. If you know how to write on PDFs, you can. Or you can just do this stuff off to the side and do some of the pictures on your own. We are going to be doing lots of sketching over the next couple of days, so you might want to get some graph paper to help with those sketches. But all of this stuff that you see here is also in Desmos, so I'm going to get you to sketch in Desmos too, kind of by hand as best we can. Okay, so this worksheet is in Desmos or in Classroom, but we're going to go through it using Desmos. Okay, so I've released a new Desmos. So if you could go in there into the new latest Desmos activity. Seemed to be in here twice. I just want to make sure I get any feedback. Okay, so you should be in Desmos right now doing the first 4 slides of the activity called Investigating Graphs of Derivatives. It'll feel like a little review of an activity we did earlier up until the end of slide 4. So if you could come back to the Google Meet, please. I'll unpause the activity in a second. All right, so just recapping what you did in the first 4 slides to make sure you're set up to do the last ones on your own. So here is the function we looked at before. 6x minus x squared, and we were investigating all the different slopes of the tangents. This is where we discovered about increasing and decreasing in max and min and positive and negatives. Now we're actually recording this down to find the derivative. So at x equals 0, the slope was 6. Then you slid this up to x equals 1, the slope was 4. And then it's obviously getting smaller and smaller as I get x equals 2, the slope was 2, all the way up until the max at 3, so the slope is 0, and then it starts to become negative and getting down to there at -2. Then we take these points and we plot them on our graph. So I graphed the first one for you, 0, 6. The next one is 1, 4. The next one is 2, 2. And the next one is 4, 0. And then for -4. So I have all these. They look like they're in a straight line, which is curious again. So I'm done plotting these. It says these points illustrate the new function called the derivative. So we discovered that in the last activity. Does the graph look familiar? And I already looked at your answers. Yes, it does. It looks like a line or a linear function. Okay. So we seem to be getting that. And here then, what you can do is, if it is a line, we know how to come up with equations of lines. So I think we can come up with an equation that represents the derivative here. So this looks like a straight line. The slope is negative, and it seems to be going down by 2's. So I'm going to start with -2x. I'm going to see if that's right. And it's not quite right because I have to add the y-intercept, and of course it goes through 6. So this is 2x plus 6. And so it turns out that the equation for the derivative is -2x plus 6. And we've discovered this derivative for this particular special function. Now, what we're going to do is I'm going to open it up, and you're going to investigate the derivative of x squared, the parabola, x cubed, the cubic, and x to the power of 4. And you'll be doing exactly what you just did here. Use the slider to get the points, plot the points on the graph, see if you can come up with the equation of the derivative, and see if you're right. Okay? So I don't think there's much more I need to walk you through right now. So we're coming up on 1:15, which is the end of period 3. So I'm going to, in a moment, let me just stop presenting here and come back live. So what I'm going to do then is release you here in a second to have your break and your period 4 work period. The practice or the homework are these 2 activities. So one, while we're in it, finish this investigation on derivatives. So come up with the derivatives of x squared, x to the power of 3, and x to the power of 4. So that's completing the worksheet. Okay, we're going to complete it on Desmos. If you can actually go and write the worksheet out, then that'd be great. But if not, at least you'll be able to experience what you're learning through Desmos. Okay, so that is your one bit of homework or work to do in the last period. The next is to go back to the dragster one. Okay, not the dragster revisited, the very first one we did. So I'll just go back and present my screen again. So what you're going to do is, you can see I've paused you right now. You're investigating the graphs of the derivatives. You're going to continue on with this and finish this Desmos activity where you do x squared, x cubed, and x to the power of 4. And then go back to the dragster activity where you can see some people are far along and others haven't quite had a chance to go off and do that. Okay, so going into Google Classroom, I'll point out the 2 things that you have to do is the Desmos dragster, rate of change, which is the first one, 1.1. So finish that one up. But you'll probably want to go and do this Desmos activity, the one we're in the middle of right now. So finish that one, go, and then go back to the other one. The other Desmos activities we've completed, and we've done everything else in here.